That's about the fluid without flow. Okay, the fluid in equilibrium. And if the fluid in flow, so we need to think about this is so-called dynamics, fluid dynamics. Okay, and fluid dynamics is very complicated issue, and it's very important. For example, to design the aircraft, you have to start with the fluid dynamics. So the aircraft can fly fast, can fly stable. Okay. If you just put some random shape there, and then it cannot fly in the air. Okay. The fluid dynamics is difficult to deal with, so let's talk about the ideal fluid. So it's kind of the simplification of the real fluid. So for the ideal fluid, we assume several things like this. Okay, they can be approximately achieved, but you can never get these things precisely. First, we want the flow is steady. Okay, so the velocity at any fixed point doesn't change in time. So along the streamline of the flow, basically says that at any time the velocity at this point will be the same. Okay, the water keeps changing, keeps flowing. Okay, every time we have new water molecule here, we assume the velocity will not change, steady flow. And we also assume we are trying to start with a non-viscous flow. Okay, so between these water molecules, this layer of streamline, we assume there is no frictional force between them. Okay, and we need to assume this is incompressible fluid. So you cannot compress it. This one is okay because most liquid you cannot compress it. And the consequence is that the density will be the same everywhere. Okay, and it's a constant, doesn't change. Finally, very important constraint is that you shouldn't have any swirl, this rotational flow anywhere. Okay, and the difference can be seen from these two graphs. This is what we call the ideal flow. So it's like streamline like this, and this is we call turbulent flow. You have a lot of swirl, okay, turbulence. Once you have these things, it will be very difficult to deal with. Turbulence problem is most famous difficult problem in physics. No one can really solve it actually. Okay. Sometimes we joke that there are two problems even the God cannot solve. One is the turbulence problem. Okay, it's too complicated. Okay, so we only consider some simple cases. Just no, we need to assume our flow has to satisfy these conditions. Now, we cannot do detailed derivation. We don't have time to do detailed derivation of all the features of the ideal fluid. But let's think about it. If we have something like that, even after all this simplification, this is quite a complicated problem compared with our previous problem, right? Our previous problem, we have only one particle, one object. But this is a fluid. It has many different molecules that are flowing all the way to that. Okay, so the new materials keep coming and keep going. So this is a very complicated problem. So usually, how can we start with this to deal with this kind of complicated problem? We can only look at the conservation law here. Okay. If you try to do the force analysis, that will be difficult. You have to do force analysis for each particle, and so very difficult. And for this problem, we can list all the possible conservation laws. Okay, you can think about. So in fact, this is a very general way to deal with the problem. Like now, when we deal with quantum mechanical system, again, it's complicated. You cannot solve exactly. So we always think about, okay, let's look at this system. Can we find some quantity conserved? And try to use the conservation law to deal with the problem. So for fluid, let's first list all the possible conservation law and examine if they can apply here. So, conservation of mass, conservation of energy, conservation of momentum, and conservation of angular momentum. That's all the conservation law we know so far. Okay. Now, but some of them may not be applied here. First, we need to identify that we cannot use conservation of momentum. Can you think about why? Okay, what is the general condition to apply the conservation of momentum? Do you remember? If you want to apply the momentum conservation, what kind of condition you need to satisfy?
That initial momentum and final momentum is equal.
The initial momentum equals to final momentum. That's the result of the momentum conservation. What is the condition to have momentum conservation?
Objects.
External force equals to 0. So let's look at, in this case, you cannot, the external force is not 0. There are several forces you cannot ignore. One force is a force to make it flow, right? Another force, in this case, is a force to confine the water in the tube or the river, right? There are some constraint forces from the wall of the tube. If we think about flow in the tube, these forces cannot be ignored, and you don't have a large internal force to make you ignore the external force, right? So you cannot use conservation of momentum. By the way, you cannot use the conservation angular momentum. Okay, two reasons. First, this is not a problem with rotation. Second, we're thinking about streamline flowing. You cannot even have this turbulence, the swirling. Okay, so it has nothing to do with angular momentum. So we can consider the conservation of mass and conservation of energy. And this will lead to important equation, fluid dynamics equation. One is called the equation of continuity. Another is called the Bernoulli's equation. That's the two equations we are going to talk about. So first, if you consider the equation of the conservation of mass, you are going to get this equation of continuity. It can be staged in different ways. Statement one says that in the same time interval, the volume of fluid enters one end of the tube interval equals the volume of the fluid leaving the tube. Okay, so I don't know why I have the interval here. And so this is natural. But due to the mass conservation, it says that how much fluid entering at one side, then you should have how much fluid leaving from the other side, if there is no leaking, right? And this will lead some statement like this. So it says that the volume flow rate or the mass flow rate is a constant everywhere during the flow. The volume flow rate can be calculated as a cross-sectional area A multiplied by the velocity of the fluid. If you want to calculate mass flow rate, you need multiply by it by additional quantity, the density. So this gives you a conservation law in this form. If you